So far, we've talked about indefinite integrals, so today we're going to be talking about definite integrals and the fundamental theorem of calculus. If f is a function on the interval a to b, then for any subdivision of a to b and any choice of x sub I star in the ith subinterval, the definite integral of f from a to b is denoted using this notation. Now notice that the only difference from this notation to the indefinite integral is that we have these things here, and these are called our limits of integration. And that tells us the interval that we are integrating across. And so that definite integral is equal to the limit as the max delta x sub I goes to 0 of the summations from I equals 1 to n of f of x sub I star times delta x sub I. Now that looks really intimidating, but basically this is what we've been working with when we were approximating area under the curve. So this represents the height of each rectangle, and delta x sub I represents the base length of each rectangle. And remember, the more rectangles we had, the more accurate our approximation was. And so basically this part is saying that we're having the rectangles get skinnier and skinnier, or the width of them or the base of them are going to 0. And that's another way of saying n is going to infinity, and we're having like infinitely many of those rectangles. If f is a continuous function and delta x sub I goes to 0 as n goes to infinity, then the limit exists, and we say that f is integrable on the closed interval a comma b. Now, this definition of the definite integral is quite complicated and is not super helpful for us when we're doing computations, but thankfully, we have something called the fundamental theorem of calculus. So after much study, mathematicians found that there is a simpler way to calculate definite integrals. So let f be a continuous function on the closed interval a comma b, then the definite integral of f exists on this interval, and the definite integral of f of x from a to b is equal to capital F of b minus capital F of a, where capital F is any function such that f prime of x is equal to f of x for all x in ab. So that's basically another way of saying that capital F is the antiderivative of lowercase f. Now, let's see this in practice because it's really useful, and it's probably why they gave it the name the fundamental theorem of calculus. It becomes very useful when we're calculating definite integrals. So let's see it in use. Example 1 wants us to evaluate the definite integral of x squared plus 1 dx from x equals 1 to x equals 3. So the first thing that we want to do is we want to basically integrate that function. So we'll have x cubed over 3 plus x, and instead of adding the constant of integration, we're going to evaluate from x equals 1 to x equals 3. You'll often see this bar notation here, and that just means that we are going to evaluate it at b and then subtract it after we've evaluated at a. So this is now equal to, and I like to put these in brackets, 3 cubed over 3 plus 3. So this thing here represents f of b, which in this case our b value is 3, and then minus 1 cubed over 3 plus 1, like that. And then this thing here represents capital F of a, and our a value is 1. So let's go ahead and simplify that. 3 cubed is 27. And and then 1 cubed, so we have 1/3 plus 1. And then we want everything to have a common denominator. So this is going to be 27/3 plus 9/3 minus 1/3 plus 3/3. And that's going to end up being 36/3 minus 4/3, which ends up being 32/3. Example 2 wants us to evaluate the definite integral from 2 to 4 of negative x cubed plus 7x dx. So this is equal to negative x to the 4th power over 4 plus 7x squared over 2, evaluated from x equals 2 to x equals 4. So that's going to equal negative 4 to the 4th power over 4 plus 7 times 4 squared over 2 minus negative 2 to the 4th power over 4 plus 7 times 2 squared over 2. All right, let's do some simplification. So that's going to be negative 256 over 4 plus 112 over 2 minus negative 16 over 4 plus 28 over 2. And that equals negative 64 plus 56 minus the quantity negative 4 plus 14. And then we have negative 8 minus negative 4 plus 14 is 10. And then negative 8 minus 10 will be negative 18. So that is our final answer. So here are some properties of integrals that we'll often use when we're calculating definite integrals. And some of these you've seen with indefinite integrals, so they, copy over when we're calculating definite integrals as well. Like number 1 says if you have the sum of two functions and then you're integrating that, you can split that up into a sum or difference. You can pull out a constant if you have that inside of your definite integral. The second two we haven't seen because they're more specific to what our limits of integration are. So number 3 basically says if your limits of integration are the same value and then you're integrating some function, then the numeric value or your final answer is going to be 0. And we can see that in a future example. And then 4 says if f is integrable on a closed interval a to b, then if you are integrating from b to a of f of x, that's the same thing as if you are integrating from a to b, and then whatever that value is, you multiply it by negative 1.